Package seal integrity is critical for today's manufacturers. For example, in the food and beverage space, faulty packaging limits the shelf life of a product. Reducing product shelf life increases waste, especially for perishable items, where package leaks can accelerate the decomposition process. For the pharma and health industries, package sterility ensures product efficacy and safeguards end users. Automated infrared inspection with thermal imaging cameras for package seal integrity testing is one application that continues to gain traction. Using infrared inspection as part of a quality control program allows for inspecting all package seals in the production line. Companies can ensure package seal integrity, promote product quality, and elevate customer satisfaction by implementing complete package line inspection. Good day, Marcus.
Hey, Dave.
How are you doing today?
Very good. It's
awesome.
Tuesday.
It is Tuesday. Yeah, it's a good day. Just finished up the Thanksgiving holidays. You had a good holiday?
Yeah. Too much food as usual.
As usual. And wrapping up the end of the year, which is kind of crazy around here at Movie Therm, isn't it?
Oh boy, yeah. I mean, I say this every year how fast time is moving, but it is accelerating and at a pace that's uncomfortable sometimes,
Yeah, I do know all too well now. And it's great to know, I have to say, but yeah, it's a busy time.
Yep.
Thank you for joining us, everyone, our listeners and those who are watching this podcast via YouTube, our watchers. This episode of the Thermal Review, where today we're talking about package seal integrity, and not just talking about seal integrity, but how you can utilize thermal imaging technology to ensure the integrity of package sealing. It's kind of an interesting and fascinating subject, and as mentioned in the opening paragraph, it's gaining traction. It seems to be growing like crazy. As more and more companies become familiar with the capabilities of thermal imaging, coupled with the importance of packaging. In fact, Marcus, I was hoping that we could kick off today's podcast by talking about heat sealed packaging. You've been doing this for a while. You know about this. I was wondering if you could explain to our listeners who aren't familiar, what is heat sealed packaging?
Yeah, I think everybody gets in touch with packaging almost pretty much on a daily basis, right? Plastics are omnipresent, paper bags, those kind of things. And then, most of the time, nobody really actively thinks about it. Like, these things have to be sealed somehow, right? Because you don't want your flour to come out of the bag when you go shopping and, mess up your car, or liquids leaking out of, your energy drinks or whatever the case may be. And so, packaging is really, a big topic for manufacturers for any sort of food items or pharmaceutical medical items. All the stuff, the product needs to be protected, and usually that's done by packaging, right? It needs to be transported and all those kind of things. So packaging is a big deal, and usually that happens obviously at the end of the line. And one big aspect of that is sealing. How do I seal this thing shut? And it's also happening at very high speeds. It's happening at very high volume and throughput. So a lot of these plastic containers are being heat sealed, and there's different methodologies out there. Most commonly, there's some sort of a heat platen that pushes down by pressure onto the package, and it has a shape of the sealing area. It could be a single straight line, or it could be a more complex shape if it's more of a rounded sort of a thing. And it's pushing down on the package, and it's providing a certain amount of heat to the foil that sits on top, or it may be a pouch that has foil on the back and on the front, and it presses down. So it's basically pressure and heat, and it's starting to kind of melt the plastic together, or there may be some pre-coated sort of an adhesive that's on the inside liner of the packaging that's just being heat activated and then bonded together. It's really a welding process in a sense, a plastic welding process. And then it goes off and typically then gets packaged. But the biggest concern there is, well, did my welding process do its job, right?
Yeah.
And there's a lot of things that can go wrong in that. It could be that the pressure wasn't applied properly. You have maybe a fluctuation in your pneumatic pressure or hydraulic pressure of your system. It could be that something didn't move properly and it kind of got stuck and now it's coming down crooked on your package, and therefore one side is kind of sealed, the other side is not. Or what we commonly see is a gumming up because these metal plates are being heated to a level where it's melting plastic. So some of the material accumulates over time on these heat platens and gums up those heat platens, and then the heat transfer is not there anymore. So even though the machine tells you, oh yeah, I've reached my sealing temperature, it's not being transferred because there's some plastic layer that's preventing it from transferring into the package now because it's gummed up. So it needs to be cleaned, but how do you know if you don't check for it? So we often see, end of line inspectors that are just like sometimes just a pouch, just squeezing the pouch to see, is air being released or is liquid coming out, just doing a test there. But you can imagine if you're doing hundreds of thousands of packages a week or something, it gets quite laborious and it's maybe not as precise as it should be. So that's kind of, where thermal imaging can come into the rescue and kind of automate that sort of inspection process there.
It's been eye opening to me, Marcus, since joining the Movitherm team. It's been about a year and a half now, but the number of packaging companies that are so focused on this package integrity. I'll just call it package integrity at this point. And I used to always think about it more so from you don't want to have leaks. You want to make sure things are being sealed properly so they stay sterile. I mean, there's those are critical factors. But in talking with some of these companies, I guess oversealing is also, and I don't know the proper term, I'm calling it oversealing, but when you glue something so tightly together that it creates a bad customer experience in trying to open the package. And we've all been there, right? Where we've had those plastic enclosed products, whatever it may be, where it's, you're busting out the scissors or a razor blade, X-Acto knife, whatever, to get the thing open so you can get to the product inside. But these companies are also concerned about that side of it as well. Like, well, we don't want to create a seal that is so strong that it creates a bad customer experience. So a lot of engineering really goes into like the perfect seal, right?
Yeah, there's two negative things that can come from oversealing. One is that you just mentioned, and I think that sentiment towards impossible to open packages is going to increase once Christmas morning comes around.
Yeah, goes beyond child proof. It's almost adult proof. Yeah.
Right. You almost need a chainsaw to open them. So that's definitely those blister packs that have these really really stiff, clear plastics that are sealed so shut. I mean, it's literally, sometimes it's impossible to even go in with scissors. It's like, literally you need like a box cutter to really cut this thing open, and then that's the danger of cutting yourself in the process. I've done that. So that's one thing. And some of the concern there is theft in the retail store, that people don't just crack open a package and remove something from it. So I understand that sort of motivation there as well. But the other part that's can also have a negative impact is if you're oversealing a somewhat more fragile package, a pouch. What you can do is you can overmelt the outer liner of the plastic, and then the seal becomes now a weak spot, because let's imagine you have a bunch of these pouches thrown into boxes, into a larger box for transport and shipping, and now they're experiencing pressure because of additional weight put on top of them and being handled and those kind of things. Now these seals can actually break open. Okay, and it's one thing to have a chips bag break open and have some chips coming out, but if you have some soapy or sticky sort of liquids in there, I've heard from customers, if they're shipping to Amazon or Walmart or the likes, if Walmart opens a truckload full of stuff and there's just one leaker, and one little pouch can ruin a complete box or even a complete pallet full of stuff, they just close the door and send the whole truckload back. And if you do this 2 or 3 times in a row, you may lose your contract.
Hmm.
They don't want to mess with it. They don't want to figure out which package has leaked, and they just close the door and ship it back, the whole thing, and it's up to you to fix all of that. So it's a big deal. Also from, like I said, the perception, customers' perception of the product itself. I mean, who wants? I mean, it's upsetting, right? You open something, or you buy something and it's leaking. Well, imagine this in a let's say you're buying a supplement over the counter, or some pharmaceutical, and the seal is open. Well, do you trust the product? Do you trust the brand? Like, what's going on? Did somebody tamper with it?
Hmm.
Is it just,
Hmm.
those things are huge concerns. And one thing you never want to do is lose the trust of your customer, right? I mean, that's just not a good position to be in. You can argue, okay, well, the cost of this product, is just in the couple of dollars range, or a few cents, even, whatever. But the damage that it might cause, people start talking on social media channels and say, "Hey, I bought this, and this is really not good, and I got a broken package, and what were they thinking?" If that's happening, that damage can go into the millions.
Yeah.
So it's really something that companies take very, very seriously.
Yeah, and while packaging is at the end of the production process, as you mentioned, or the manufacturing process, it's the first part of the customer experience, right? And it can set the
Right,
tone. It'll set the
right.
tone for how that customer reacts and responds to that product, how satisfied they are with it, and the product itself could be intact. It could be just fine. But if the unpackaging experience is a miserable one, it's hard to separate the two.
Right.
Yeah. So you mentioned a couple different types of packages. I heard blister packs, and then you mentioned pouches. Um, can you what are the different types of heat uh, heat sealed packages? What are they? Because apparently there's obviously more than just one.
Right. They come in all kinds of shapes and forms. Essentially anything plastic, and even a lot of paper, carton type things are heat sealed. And there's a few other categories, even cardboard boxes. Like, if you pick up a 6 pack of beer, it's a cardboard box, so there the heat sealing is really done using hot glue most of the time. But
Hmm.
even there, the question is, well, has it been glued properly? Because if you pick up a 6 pack and the bottom falls out, that's upsetting as well, right? And again, you're going to start blaming the brand. You're not going to start blaming anything else. And who wants to have a bunch of beer cans exploding on the floor, or bottles?
Yeah.
So those are things. Then there's paper bags. Let's say you pick up your favorite flour or something from the store, something like that. So they typically and it come also in different weights, right? All the way up to the let's say you have a bakery and you're going up to the 25, 50 pound bags. But those typically have a couple of layers in the packaging. They have like the very strong paper, almost cardboard like paper on the outside, and then on the inside they typically have a plastic liner, because they want to make sure that you have a moisture barrier, so that your product doesn't clump up and get moist from the environment, so you can store it at normal conditions.
Yeah.
um, and so they have typically that moisture layer, so it's a plastic liner on the inside, and that is being essentially melted together by applying either like what they call a band sealer. It's kind of a band that has a heater built in, so that can actually the bag can come down a conveyor belt, and it's being sealed on top while it's moving. That's a typical thing. We've worked with companies that have used a ultrasonic sealer, So they have jaws that are clamping on top of the bag, and they are ultrasonically being vibrated, and that's causing friction again on the inside, and it's creating heat and therefore sealing it. So those are things we have in medical applications. We have seen even RF welding, where they have a softer material to a harder material being welded, and they're using RF welding and RF energy that goes in and excites the material and creates heat in a focus spot. Most of the sealing though is done with heat plating of sorts or a band sealer, and then there's another category, which are bottles that have these, you open up a plastic cap from the bottle, and then underneath you have this silver foil. And sometimes you have a little pull tab on it, and sometimes you just have to peel off that, let's say it's your coffee creamer or something or whatever, and you're trying to peel off that silver seal. And again, that's also because the cap in and of itself does not seal the bottle properly. So they put the safety freshness seal or whatever they call it on top. And that's actually an interesting process, because the majority of those bottles are being sealed by, first the bottle comes down the conveyor, then the bottle is being filled with the product, and then they have a capper that screws on the cap on top of the bottle after the filling process. And the capper with the cap has actually a liner that silver foil is already inside the cap by the time the capper puts the cap on. So at this point, that silver foil is not sealed against the mouth of the bottle yet. It's just being capped on and screwed down. So the question now becomes, well, how are you going to seal this now that the cap is on? Do you have to remove the cap again? I mean, that doesn't make sense, right? So they run this under an eddy current coil, an induction heater. And the listeners may know this sort of concept from these stovetops that are not getting warm by themselves, but you put a metal pot on top, and it's basically warming up with magnetic currents. It's warming up the metal, and that's the same concept being used there. And because of the pressure of the cap that pushes down on that seal, that induction heater is now heating up that foil to a point where, again, that adhesive that's on the underside that's facing the mouth of the bottle is now being heated up to a melting point, and because of the pressure of the cap, it's now sealing against the bottle. But now the question becomes, okay, great, I didn't have to remove the cap. How do I know the seal is on? Do I have to remove the cap? And literally people are doing that. And sometimes on spot checks, sometimes on every single bottle, and it's ridiculous from a process point. So what we have is actually a bottle cap inspection system that can see that heat radiating from that sealed aluminum foil through the cap, and we can actually tell, based on that heat signature, was that seal applied to the bottle properly, right? So that's our bottle cap sealing solution, if you will. So that's a very special package sealing application. And then there's all kinds of challenges with that. Then we have blister packs, where you have, most folks know this from, running to the store and getting, let's say, one of those cheap razors or something like this. You see a clear plastic blister on top that is basically vacuum formed around the shape of what's in there. So it could be a razor and then 3 razor blades with it next to it or something like this. So it's a nice display. You can see already what's in the package, and the backing maybe a piece of cardboard or something like this that has some pretty print on it, and that it's just being sealed against it. So those kind of are things. Then they have pouches of any sort of things for, like, vitamin powder in there, or even liquids. There's satchels. Those are typically the tiny little pouches, if you will. And all of those need to be sealed, right? And then regular containers too. When you pick up your grated cheese or something, you have a plastic box, if you will, with a foil on top, that sort of thing. And you peel away the foil, and all of this stuff needs to be heat sealed somehow against it to form a proper bond, right?
Yeah. So Marcus, you started to talk a little bit about thermal imaging or infrared imaging inspection a little bit in that bottle cap, induction bottle cap application, which is right. Brilliant. I mean, you still have heat and pressure, but the heat, you're not applying heat to create that seal. You're applying a current, right? That eddy current.
Yeah.
And then even in that ultrasound or ultrasonic sealing, that's quite interesting. You're using friction, if you will, to create the heat.
Yeah.
But you're still utilizing this heat sealed process. How before I ask you to kind of talk a little more about infrared and kind of the physics and why does it even work for inspection, how do companies, I mean, you kind of mentioned this, that sometimes it's quite literally someone physically looking at, how do they test these things currently? Is it all visual?
That's a good question. Yeah, and it's a huge challenge. So the biggest concern is always a leak, right? And a leak could be
Hmm.
a gas leak, a very tiny little pore that's open on the sealing area. And that can be caused, as I said, it can be caused by an imperfect seal to begin with. It could be a material imperfection. It could be a little fold over. It could be that your sealer wasn't set up right or didn't apply the right pressure or even pressure on the packaging. Or what quite often happens is that you have what we call part and seal. So maybe a little bit of the powder spilled into the sealing area, and now you're trying to seal it, and it prevents it from melting together, right? Because there's a little powder in there. It's like kind of having, sand in there, if you will. Or it could be a piece of cheese stuck in there, or something that's just preventing it from sealing, and then you can have the package contents spoil. Really detrimental for medical applications where you have a sterile package, you have a sterile barrier. That's a huge no-no. I mean, you cannot have that happen. I mean, worst case scenario, you cause an infection or the patient dies. I mean, those are things we have worked with. Has a bad rap nowadays in the news, obviously for correct reasons, is fentanyl, which is a synthetic opioid. It's 100 times stronger than morphine. Well, we have worked on a packaging line that fills what they call transdermal pouches. So what it is they put a gel containing fentanyl inside the pouch, and then you get this. You glue this. You stick this onto your arm, and it has what they call a transdermal membrane on it. So that membrane is very specifically designed to only dispense a few micrograms of that gel into the skin per hour. Okay, so it's very important that is all fully intact, because if you have a leak, you may overdose and you risk the patient, so those
Yeah.
kind of things. So there's some super mission critical applications there, that go beyond, just, I have a spoiled package and customer perception. I mean, that's really like, human safety, patient safety sort of things, especially also with the medical sterile packaging and that sort of thing as well. So there's a lot of sort of things that go on, in that direction that need to be considered.
So how I don't know if you can talk more about that patch before inspecting with thermal. What did they do?
Yeah.
What,
So leak detection, right? So there's what they call a leak decay detection, right? So they put a
okay.
package in there and they put it into a vacuum chamber.
Okay.
And the idea is that if there's a leak, it's gonna, something's gonna leak out of the package, right? And then they can measure based on the pressure change in the chamber. They can measure whether something is leaking. But the problem is, for a very small leak and a high throughput line that doesn't work on 100% inspection, that's just
Yeah.
occasionally you can look and look at that sort of thing, right? So that's just a spot check at best. And then that doesn't really address anything other than telling you, oh, there's a leak. So if you have a continuous problem where every part now comes out with a leaker, okay, then you have something to work with. But if it's the occasional package, whether you do this or not, you may miss it anyways.
Yeah.
So that's not very effective with respect to doing 100% inspection. There's also ultrasonic technology out there that tries to measure the seal. Again, from a spatial resolution and everything else, those are all indirect measurements of what went wrong during the thermal bonding process, right? Those are all indirect measurements. Whereas what we do with thermal imaging is the thing is here, in terms of process control, what are you concerned with your sealer? You're concerned with that the process variables that you set up to do certain things that are being kept within certain variations, right? Certain tolerances. So one thing is the sealing temperature. Somebody, based on the type of material and the melting point of the adhesive or the plastics or something like this, has determined, okay, we got to run this at 275 degrees, let's say. Well, so you have a thermocouple on your sealer and it says it reads 275. Great. And then you need a certain amount of pressure, and you may have feedback on that, right? You know what your pneumatic pressure is, or hydraulic pressure or something, or even mechanically with a servo drive or something. So now you're like, okay, I have those two parameters that I can measure as feedback whether that has happened. That's the input to your process for the sealing. What you do not have is the actual feedback from the actual package now that says, well, has it been properly applied? You assume that it has, but has it been? Right?
Yeah.
So now we come in and we give that direct feedback from the material science and look at it and says, yes, the temperature has been reached. Therefore, now you have the confidence it has been, the bond strength has been properly applied. And that's the wonderful thing about thermal imaging. Now you have the ability with technology to make the actual thermal weld process visible, and not just visible in a qualitative manner, you can also quantify it. So what we do really, we take a lot of statistical data and we call it the thermal fingerprint, because every package and every sealing line has the unique fingerprint, like a human fingerprint in a sense. And we analyze that, and we recognize that that's a given, based on the design of everything, based on the packaging design, based on the materials, based on everything that's happening, and the package that's being exposed to, you're creating a certain heat signature across that seal.
Hmm.
And there's a known good range, okay? And then there's a known bad range. And that's what our system then essentially determines and makes sure everything has been done properly. So what that allows you to do, as I said, what the thermocouple will absolutely miss is if you do have a gummed up sealing jaw or something like this, it will not measure that because the metal has been heated to the right and proper temperature, but it was not able to apply that to the package. There's no feedback for you unless you measure after the fact, of after you have sealed, right? So that's the sort of thing that we can solve with thermal imaging. That is an absolute direct feedback, and we can do this at the full speed of the packaging line. So it's 100% every time.
Brilliant. Yeah. So you're I love that description of the thermal, fingerprint. That makes that I can very much relate to that. If you've ever seen the demo of putting a hand on the wall and removing it, just there for a moment, and then looking at the wall with the thermal camera, you actually see the thermal handprint left behind, created by that conduction process of you touching the wall. So that's essentially what you're doing here, right? You're looking at the residual heat that's left behind from the sealing process to determine how effective that seal is. Is that
Correct.
right?
Yeah.
Okay.
And as part of that, we actually do a cross correlation study, because we have to determine exactly that, because we are some time removed from the sealing process. Ideally, we want to be like within a second or two to make sure that we still get the most information out of the package. And heat has the tendency, based on thermodynamic laws, to go from a high energy state to the low energy state. So wherever the heat was applied, it's now starting to, the moment the jaws open up and energy is not being put in anymore, now the higher energy state, in other words, the hottest portions of the seal are now bleeding into the colder portions. And that starts instantly, right?
Yeah.
And especially if you have a pouch material that has an aluminum foil inside, that even accelerates that, because metal is a good heat conductor, right? So we want to be right there when that happens, so we can assess what's happening on the seal. If we wait too long, it's all kind of gone and blurred out, and then this like diminishing returns in terms of determining, is this good or is this bad, right? So you want to be right there. And that's exactly what happens. So we can actually see where was the heat applied, was enough heat applied, and it's basically an offset from the sealing temperature to the point in time where we measure. but there's a direct correlation now that we can discern there and say that's still good or that's bad.
Yeah. Okay, so a very critical point, it sounds like then, is the camera positioning to, or relative position to the actual sealing process where that heat was applied. And sounds like being closer, as close as you can be to that, is going to be produce the better results, because of just things
Right.
want to reach steady state. They want to go back to
Yep.
equilibrium, and so that that heat will, like you said, go from the high temperature to low temperature locations, or no
Right.
heat locations. Yeah.
It's yeah,
What
it's
what
it's critically important to the process for sure.
what
Yeah.
are some of the other critical considerations around utilizing infrared or thermal imaging technology for this heat seal inspection? What are some of the other things that you need to be aware of?
Yeah, so we have determined that the inspection location, which translates into time from sealing, right? So the further you're
Mm,
away, the more time has passed, right? Now, physical constraints on the machine. I've seen folks that have like a polycarbonate sort of covers or something over things. The human eye can see through this, but the camera cannot. So,
yeah.
and it's not a big deal, but you have to either cut a hole in it if you have to look through it or something like this, or put an IR window in it or something like this. Other physical constraints. A lot of these packaging machines are very physically constrained. There's a lot of stuff around it. So we have to make sure that we have a clear line of sight. What we want to make sure is that we can look straight onto the seal. We don't want to be at an angle, because
Mm,
then again we lose information, right? So, I mean, plus minus 5 degrees is probably not a big deal, but if you're going a lot further at an angle, again, you're reaching diminishing returns there somewhere. Okay, and that has to do with people that are familiar with thermography. Is emissivity has a dependency on angle, so the steeper the angle becomes, the 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 more the impact is there from the emissivity side of things. A lot of things are being reflected away from the camera rather than being captured by the camera. So those are things there. We look also at the way the material behaves with respect to the camera. So there's a vast variety of different materials, different prints. Some material is very shiny to the thermal camera. It may not be shiny to the human eye, so that's a lot of folks get
mm,
confused by that, and it goes both ways. Sometimes you're like, oh, there's no way you can measure this, and then you look at it with a thermal camera and like, oh, that's no problem. Or you look at it and says, oh, that should be no problem, and you look with a thermal camera and it's shiny and reflective all over the place. So that's why we always put some sort of a feasibility study up front to make sure that we have a solid and robust sort of an application, because there's no point in trying to solve something where you have to battle physics. I mean, there's just sometimes the answer is sorry, this is not going to work on this material. End of story.
yeah. You
And
can't cheat the physics.
right, and nobody gains anything from it. Whether I don't want to have a system out there that doesn't work. I don't want to have an upset
Yeah.
customer, and the customer is not being helped because they can't automate what they want to automate there. So those are critically important as well. Those are like the key things to consider.
Hmm.
You know.
You mentioned, I mean, you talked briefly about bottle cap, and the thing that's, well, with bottle cap, you're literally putting the cap on top of the seal.
Hmm.
So I know there's some special considerations for that kind of inspection. Maybe you can explain that. Talk about that a little bit.
Yeah, the physics there are very interesting, and they're changing quite a bit from a looking at a package seal specifically on as the first surface, so to speak, right? So when we're looking at a bottle cap, we no longer look at the first surface of the sealing area, right? Where the heat actually, because of that inductive heating process, they happen underneath the cap. So the
Yeah.
plastic is not being heated up at all. Well, later on in time, indirectly by the heat of the seal, but not directly, because plastic obviously does not have any magnetic sort of properties in it, and therefore it's not being heated. So that creates an interesting dilemma for thermal imaging, because all I can do if I use a camera typically is look at the surface of the plastic, and all I see now is what's the surface temperature of that cap. Okay, so depending on the cap design, if it's a simple cap, which is really just if you look at it from a cross-sectional view, it's just a, kind of a inverse U shape, right? And it's
Mm-hmm.
very simple. Let's say there's no raised lettering or embossed lettering on it. It's just a plain, smooth plastic cap. There's still a little bit of, or there can be a little bit of an air gap underneath the cap to the foil that we're looking at. So if that's the case, the heat needs to now transfer through the air into the bottom of the plastic cap and kind of propagate through the plastic thickness to the surface of the cap, right? So this works on simple cap designs because typically the simple cap kind of touches the seal.
Okay.
Okay, so the transfers rather quickly, and then you can look at this. But it changes altogether if you have a more complex cap design, and that's typically the case with, they call them CRC caps, child-resistant caps.
Hmm.
Everybody knows them, where you have to kind of push down on the cap, squeeze it in a funky way, and then kind of open it, because it has a little ratchet thing. So when little kids trying to open something, and it could be, let's say there's rubbing alcohol in there, or like a corrosive thing, or whatever the case may be, that's dangerous, or some cleaning liquids that's, you don't want to have a little baby accidentally swallow or something. Those caps actually come at least in two parts, if not more, where there's an inner cap design and an outer cap design, right? That ratchets together and everything. And now you have a much larger air gap in between, and you have another layer of plastic in between. So you can imagine, now heating up the seal, the heat has to travel through two layers of plastics. There may be also even dissimilar plastics, and then all the way to the top. So if you look at this thing, you can actually not see anything until you're 10, 15, 20 seconds down the line. By that time, because of this heat transfer, most of the information is gone. So you have a very poor representation now of what actually has happened during the sealing process, because so much time has passed and all the energy has blurred and gone away. It's next to being useless if you use that approach. But
Yeah.
so you need to employ the big guns, if you will. You need to switch to a more sophisticated camera that can actually partially see through the plastic. Okay, and that's unfortunately gets a little bit more expensive, or quite a bit more expensive. And this may also drive certain customers outside of the affordability range, right? Because it's like every problem in automation has a certain pain factor and it has a certain price point.
Hmm.
Meaning, what is the cost of not implementing a solution, right? That's what the customer needs to ask themselves. Like, if I don't address this, how much scrap, let's say, do I have? How much upsetness do I have in my customers? Well, however you want to quantify this, there's a certain price point, or how many people do I need to employ to manually check everything? There's always a price point. There's always a cost to not implementing a solution and automating that inspection process, right? So that's really what you have to now weigh against the cost of implementing the solution, right? And they need to be in alignment. Ideally, the return on investment should be on the order of 12 to 18 months, maybe 2 years, for the US market. And that's pretty much the pain factor that companies are willing to invest in. If they get their money back within that time period, then there's a business case. If it takes longer, a lot of times customers don't want to go there,
Hmm.
which is interesting because I'm coming from Europe, and we have partner companies in Europe. The thinking there is more long term. You can actually see the return on investment. If it's 3, 4, 5 years even, they still invest in technology like this, because for the long run they're going to be better off. So they have a longer term sort of vision for those kind of things. That's kind of an interesting return on investment sort of a philosophy here in the
Yeah.
US.
Yeah, that is. And this has always fascinated me with infrared technology compared to, what we see visibly with our eye is there are materials that will appear opaque to our eyes, but
Mm-hmm.
in other wave bands, they could be transparent, semi-transparent, or vice versa, like you mentioned, that shield that we could see through in the visible spectrum, but thermally we can. It's opaque. It's
Right.
absorbing all the infrared energy, so we can't see through it. And for this bottle cap application, utilizing a camera that has a wave band that allows you to have some transmission through to see that seal underneath. It's fascinating. It's amazing. It's physics. It's science. We can't cheat it, but we can actually leverage it to our advantage in certain instances or cases like this,
Right.
so that you can see that seal underneath, if you will, the cap,
Yeah.
which is pretty fascinating. Yeah.
It
Um,
is. It is. Yeah.
so, Marcus, other considerations for this type of inspection. I'm assuming that in some instances it can be an industrial environment. How does that impact thermal inspection or infrared inspection, the environment that the cameras are in?
Yeah. Good point. So obviously that is a strong consideration. Depending on what you're filling, the environment may be impacted by that, right? So if you're having liquids, stuff can splash, right? So you want to make sure that the camera is protected against that, not that you're shorting out the camera because some liquid ingress or something like this. So if you have powders,
Hmm.
it gets tricky because obviously, again, you don't want to have powder settling on the lens of the camera, and causing an annoying maintenance issue. Although sometimes that's not avoidable, but then it goes sometimes further. If you're doing a flammable liquids, let's say filling of alcohols or something like this, now you're getting into the realm of explosive environments, and so now you got to protect your equipment and make it what we call X-proof, in you know in our lingo, if you will, explosion proof. So what that means is, and there's a whole industry around that sort of thing. So let's say we have been with a food manufacturer that does flour. So flour can actually be an explosive at the right conditions if you have the right density of flour particles floating in the air, and you may have a static discharge somewhere or a heated element that's warm enough to ignite the particles of the flour. You can have a pretty nasty explosion happening there.
That's
Okay.
amazing. I'd never think that, but
Yeah.
wow. Yeah.
Yeah. Or grain silos or something like this with all the dust coming. I mean, those things are classified as hazardous areas with respect to explosion possibilities. So there's really a couple of different things you need to do, um, and kind of adhere to the regulations there as well. So what we do is we have the ability to deliver the cameras in an X-proof enclosure, and there's really two methods. Well, there's three methods for explosion proofing. One is the explosion prevention, and that's typically what we utilize. We use a pressurized system. So we pressurize. Actually, it's purge and pressurize. First, you purge. What that means is you're exchanging about 5 times the volume of the inside of the enclosure that you're purging. This could be the control cabinet that houses a flat panel PC, HMI, that sort of thing, and all the
Hmm.
electronics. The other thing is the actual enclosure for the camera that houses the camera. So what you really want to make sure is that none of the flammables can come in contact with any electrical stuff that can spark or it's getting too warm, right? So because those are potential ignition sources. So you want to
Okay.
separate the environments. The way you do this is you're doing a purge before you turn the electricity on, that anything can happen. You purge 5 times, you exchange the volume of the enclosure. Once that's done, you're just making sure that there's nothing in there to begin with when you turn things on. Then you turn over to the pressurization mode, and that just keeps a slightly above ambient pressure inside, so that from now on forward, even if there's a slight leak on the enclosure, nothing can ingress into the enclosure. And there's special explosion-proof controllers that we equip our equipment with in those conditions. Um, you know that make sure that happens, right? So that's the explosion prevention. There's also what we call an explosion containment. Those are the people may have heard about NEMA 12, NEMA 12X sort of enclosures. Those are the ones that are super, super heavy duty, thick walled and a bolt every inch and all those kind of things. That's basically saying, like, if there is an explosion inside that enclosure, it is not going to break apart. It's going to stay put. Okay, the explosion happens inside and it's just going to go boom, and that's it. And
Okay.
also another requirement of that is that no ignition or no spark can leave during that explosion. No flame, no spark can escape that enclosure during or after the explosion. So that's the explosion containment, which we typically don't use because the gear's expensive and it's just monstrous. That's being used in oil and gas quite a bit. It's very heavy, and it's usually, doing that in stainless steel in food environments, it would be outrageously expensive and all those kind of things. That's why we, choose and opt for the explosion prevention. And then there's another third method, which is using intrinsically safe equipment. That is basically every electronic component, whether that's in a relay or PLC or this and that, you can get them, not everything, but some of them you can get intrinsically safe. That means these are electronics and power supplies that are encapsulated. They basically have poured in an encapsulation material, like a resin or something like this, and that completely encapsulates all the electronic components and prevents that from happening. Again, those things are very expensive, and you don't typically get everything you need in that form factor. So that's why our fallback position is typically the explosion prevention with purge and pressurization, if that makes sense.
Okay, that does. No, thank you. Okay, so Marcus, we're getting close to the end of our podcast for today, but I was hoping you could discuss or maybe share with our listeners, not only being able to identify rejects, if you will, and do 100% inspection, which sounds amazing, right? Versus that one-off sampling process or approach that we talked about earlier. But are there advantages are there advantages beyond just being able to identify rejects where an infrared or thermal imaging inspection system could be useful to a manufacturer or producer? What are some of those other advantages?
Absolutely, and I'm glad you brought that point up because that's often overlooked when people are shopping around for solutions. They don't consider the upstream benefit of a system like this, right? So especially going back to the ROI calculations, they're looking at it from okay, how much does it cost so that I can reject the bad parts? End of story, right? But that's a very limited view of what this technology really can do for you. What you should consider in addition is what additional benefits can this technology bring, right? So we can do trending, like going back to the example of gumming up your heat planes, right? Well, since I'm using a thermal camera, I can now trend that. And it's not just like one day it's working, one day it's not. It's a gradual degradation of the heat. And while this is going on, this heat sealing is still happening, but it's becoming weaker and weaker. So I have a way to predict when this is causing an issue. So now I can do a scheduled predictive maintenance session and say, hey, you know what? It's best that you clean this up during the next shutdown so you don't have an unexpected shutdown. Nobody wants an unexpected or unscheduled shutdown because that's very disruptive. You may miss your delivery schedules and all those kind of things, right? Nobody wants that. That's not a good position to be in. It's a very reactive position to be in. You want to be proactive. So this technology allows you to be proactive by actually predicting if something goes wrong to a certain degree there. Another thing that is sometimes underappreciated, I think, is that we come in and the first time in its existence of the manufacturing line, typically we provide the customer with statistical data of their process capability with respect to sealing. What that means is like every process has a certain process capability. It's usually a Gaussian sort of distribution of its capability. And you want to keep that in the mean, and you want to kind of have the distribution as tight together as possible. Well, surprise, surprise, often when we measure things, the sealing process is by far not as tight as the customer assumed it would be. And now we see temperature variations sometimes on seals, like I have seen 12, 15, 20 degrees variation. And then they're looking at this, and then the first thing is like, oh, there's something wrong with your system. There's something wrong with your software. It's the first assumption. And I'm like, no, that's really what's happening here. And so then the aha moment comes, and like, wow, like we didn't know it was that bad. And you don't want to run something that has such a loose tendency of drifting to the left and to the right, being too cold, being too hot, and being non-uniform, because that's just asking for trouble, right? So now the question becomes, okay, what can I do with this data to now tighten up my sealing process? And we have done that with customers to say, like, look, your left corner is always a little colder than it should be. Like, what's going on there? And they found out that they had a misalignment on the sealing, and they're like, oh, and it was just, if you take out your adjustable wrench and get it adjusted, and now it's like way more uniform, and voila, you have already improved your sealing capability and uniformity and capabilities and everything else, and your sealing quality, right? So you're already preventing issues from happening by just feeding back what you're learning from the inspection process upstream and starting to improve your process. Yeah. And that's what I'm saying. So this tool can be used not just to kick out the bad parts, it can be used to actually help you improve and tighten up your process, and how wonderful is that? And, that should be considered in the value proposition of these systems. Is like, it's more than just telling you what is bad. It's like, hey, you can actually improve what you're doing. Like who wouldn't want to improve? And often at very little cost. It doesn't have to be a redesign of the sealing system. I mean, it could, if it's really bad, but for the most part, those are little adjustments, and now you have that direct feedback of what the impact is on the ceiling. So that's I think is a huge sort of an adder there, and then there's another wonderful addition here. You have statistical data of your process. Why not feeding that into either an existing system? A lot of folks have existing monitoring systems or historians or something where they feed information in, and keep track of that, doing your batches, doing your weekly, monthly meetings, and just make sure, hey, yeah, you know what, we're running a tight ship here. Everything's working wonderfully. Or we have, in the third shift, we always have these weird fluctuations. What's going on, So, I mean, that sort of thing. So there's so much information being delivered above and beyond just kicking out a bad seal,
Yeah.
So I think that's where the additional value comes in for, about implementing a solution like this.
That's awesome, Marcus. And the data's there. I mean, you are
Right.
collecting it. It is there. Why not use it to do those things, improve the process, improve the efficiency and effectiveness of your process, and then also eliminate surprises. That's brilliant.
Right.
Being able to leverage that. So I thank you for answering that. So it's more than just rejects
Yep.
at this
Definitely.
point. There's greater impacts. Well, Marcus, thank you again for your time today and for answering these questions about this thermal seal inspection, utilizing infrared technologies to ensure seal integrities. And it's true. It's all around us as consumers, right? Just about everything I put my hand on is packaged.
Right.
So for those of you listeners who want to learn more about this thermal seal inspection utilizing infrared technology, Movitherm has an off-the-shelf solution that's called TSI, Movitherm TSI, which stands for thermal seal inspection. You can learn about it on the website. There's some knowledge-based articles around it. I think there's even a webinar, Marcus, that is recorded that you hosted a couple years ago that's available there, and some new video content as well. If you want to learn more, I invite you to go there. And if you can't find what you're looking for there, give us a ring, give us a call. reach out to us, and we'd be more than happy to talk to you about your process. And Marcus mentioned earlier feasibility studies, which are critical to learning whether or not an inspection solution is going to work for a particular application. It's great because it eliminates the risks, if you will, or mitigates the risks. And we're available to answer questions about that and even set up feasibility studies if that's a step that one of our listeners would like to take. But that wraps it up for today's episode of the Thermal Review. Thank you for our listeners. Thank you for those who are watching via YouTube. Again, we invite you to, you can even go on our website and see some of our previous podcasts and on our YouTube channel as well. Marcus, I'll hand it off to you. Any final remarks or comments for our audience?
Yeah, I hope this brought some value to folks that want to learn about package seal inspection. And second that, please make sure that you subscribe to our podcast on your favorite platform, and also subscribe on the YouTube channel. Just type in Movitherm and you'll find it all. And so that you get notified when the next podcast is being released, and any other videos that we're doing to help educate you out there.
Thank you so much, everyone, and happy holidays to everyone as we approach that season, and a happy new year.
Yep, same here.